IBM and UC Berkeley have published a paper on a new quantum computing breakthrough in error mitigation. Using a 127 qubit IBM Quantum Eagle processor versus supercomputers located at Lawrence Berkeley National Lab and Purdue University, IBM Quantum and UC Berkeley have been taking turns running increasingly complex physical simulations, checking each method against an exact brute force classical calculation to test whether noisy, error-prone quantum computers were useful for calculating accurate results for certain kinds of problems. Eagle would initially return exact methods, and as simulation complexity increased, both teams felt confident that Eagle was still returning answers more accurate than the classical approximation method, even in the regime beyond the capabilities of the brute force methods. At first, the team amplified the effects of the noise by using the same technique to control qubits, called pulse stretching. However, this method wasn't scalable. Noise amplification was the final piece of the puzzle. By means of a learned noise model, one could manipulate and amplify the noise more accurately, applying classical post-processing to extrapolate down to what their calculation would look like without noise, using an error mitigation technique called zero noise extrapolation. Okay, let's begin. Next up, we have a paper by Contextual AI called Computer Vision Through the Lens of Natural Language. So LENS here stands for Large Language Models Enhanced to C. A modular approach that leverages LLM as the reasoning module and operates over independent vision modules. So it does this by first extracting rich textual information using pre-trained vision modules such as contrastive models and image captioning models. Subsequently, the text is fed into the LLM, allowing it to perform object recognition and vision and language tasks. LENS eliminates the need for extra multimodal pre-training stages or data, bridging the gap between the modalities at zero cost. So LENS consists of 3 distinct vision modules and 1 reasoning module. These components are as follows. So they have the tag module. Given an image, the module identifies and assigns tags to the image. To accomplish this, they employ a vision encoder clip that selects the most suitable tags for each image. The next module is the attributes module, which utilizes this module to identify and assign relevant attributes to the objects in the image. The vision encoder clip classifies objects based on the attributes vocabulary generated. And then they have the intensive captioner, which they utilize an image captioning model called BLIP and applies stochastic top case sampling to generate n captions per image. And they have the reasoning module, which they adopt a frozen LLM as the reasoning module, which is capable of generating answers based on based on the textual descriptions fed by the vision modules, along with task-specific instructions. Now, the method used is given an image I, LENS leverages the vision modules to extract all conceivable textual information T that can describe the image, encompassing objects, attributes, and captions without limiting it to specific task instructions. A frozen LLM can process the generic prompts T concatenated with task-specific prompts and perform object recognition or visual reasoning tasks. LENS is very competitive even when compared to significantly larger and more sophisticated systems, such as like Flamingo and Blip2 and Cosmos, to the extent of outperforming these systems in most experimentation. All data is in zero-shot settings, as there is no performance improvement with few-shot settings. However, LENS was most accurate when the tag and attribute models were used in conjunction, having average accuracy with tags alone and performance drops with attributes alone, because it is component dependent. Its limitations hinge on the modules and models it leverages. Next up, we have textbooks are all you need. So this paper has really been making the rounds on Twitter. So it talks about Phi1. Phi1 is a transformer-based LLM with 1.3 billion parameters, which was trained for 4 days on 8 A100s using textbook quality data from the web, around 6 billion tokens of data, and synthetically generated textbooks and exercises from GPT 3.5. It trained for roughly 8 passes over 7 billion tokens, slightly over 50 billion total tokens seen, followed by fine-tuning on less than 200 million tokens. Phi1 attained a 50.6% pass at 1 accuracy on human eval and 55.5% pass at 1 accuracy on MBPP, which is one of the best self-reported numbers using only one LLM generation. Code textbook, the combination of filtered code language and synthetic textbook dataset that was created and used in the pre-training phase to obtain a base model. This model, Phi1 base, already achieves a competitive human eval performance of 29%. Code exercises is the 180 million token synthetic exercises dataset to fine-tune Phi1 base to become Phi1. Code exercises consist of complex, diverse, self-containing problems, pushing Phi1 to understand concepts instead of memorizing techniques. After fine-tuning, the model exhibited a substantial improvement in executing tasks that are not featured in the fine-tuning dataset, such as managing intricate algorithmic tasks and using external libraries. Phi1 was able to demonstrate understanding of logic and semantics, while Phi1 base failed to follow the logic of tasks and made up meaningless function calls. To minimize bias and leakage, new evaluation problems were created by a dedicated team that did not access the code exercise dataset or the final model. To understand the boost in performance, they pruned the code exercise dataset by removing files that are similar to those in human eval. This process was a strong form of decontamination and still observed strong performance on human eval. Even after pruning more than 40% of the code exercise dataset, the retrained Phi1 still outperforms StarCoder, which has around 15.5 billion tokens,